All right, so our next talk is by Zongheng and Shivaram. Zongheng is a third-year undergrad in the AMP Lab. He's been working in the AMP Lab for over a year, doing some really great work on SparkR, as you're about to hear about. Shivaram is a PhD student in the AMP Lab. He is sort of the Swiss Army knife of Spark. He's a core Spark committer, working on SparkR, working on his pipelines project, and working on distributed linear algebra, doing a lot of great stuff with machine learning and systems. So.
Thanks, Amit. Can everybody hear me? This is good? OK. So I'm Shivaram, and today I'm going to be talking to you about SparkR, which is this project to enable interactive data science at scale. So as members attending AMP Camp, I guess all of you are by now very familiar with the system Apache Spark and why it's a very popular system to do like big data processing. Some of the reasons that make Spark such a useful system is that it's really fast. It has like high performance. But more than high performance, it's also scalable. So if you add more data or add more nodes to your cluster, your performance, you can get better and better performance. But other than that, also, it has a very flexible programming API. So it's sort of easy to describe your computation and to execute them on a large-scale cluster. But another popular project that many of you might have heard about is this project called R, which is a programming language and a framework for doing statistical computations. And, and there are many nice properties about R as well. It has a lot of inbuilt functions and like packages which support commonly used statistical methods. And also, in addition to being like a processing framework, it also allows you to do visualization. So there are many add-on packages that helps you visualize your data, and thus you can do some end-to-end like data science stuff using R, where you load some input data, compute some statistics on it, and then you visualize what are the characteristics of your data. So the goal of this project is to put together the good properties in both of these projects, which is in Spark and R, and that's why we named our project SparkR. And in some sense, what we want is we want the scalability and the flexibility of Spark, along with the statistical packages and like the visualization support that R gives us. And we believe that putting these two things together can enable this kind of end-to-end interactive data science. So in today's talk, I'm going to be doing three things. So first, I'm going to be presenting the SparkR API and giving you a brief overview of how you could use SparkR. Following that, we'll see a live demo in which we actually run SparkR on an EC2 cluster and show how you can combine like data processing using Spark and some of the properties of R. And finally, at the end, we'll delve a little bit into the design details or what goes on underneath the covers to enable such a thing to be built. And the last thing is that we will also be doing an exercise on SparkR today, and so you can get a feel of how it is to use the system. So at a very high level, the main abstraction that is a part of Apache Spark is this notion of an RDD, or a resilient distributed data set. From a user's perspective, what an RDD is basically is that it's a parallel collection. So you have a number of machines, and you have a data set, which is like a list, and it's partitioned across these machines using some partitioning method. And in addition to having such a data structure, what the Spark API gives you is that it gives you a bunch of transformations. And these transformations include operations like map, filter, group by, and reduce, and so on. These transformations take an RDD and return another RDD that is the result of the transformation. But in addition to transformations, you also have these actions, which go from your RDD to some output that you can ship to the external world. So for example, you can save your RDD out to a file using a method called save as text file, or you can count the number of elements in your RDD using count, and so on. And these actions are the ones which trigger jobs that Spark goes and executes. So we took a moment to think about how can we put together R and RDD, and what would we get if we tried to do this? So one answer is that we could get an R2D2. Kind of fits really well. It was really tempting to name our class R2D2, but we decided not to do that. What we instead decided to do was to call our class RRDD, which is kind of similar. And so if we introduce this package called SparkR, and inside the SparkR package, the RRDD is a new data structure that we introduce, which is similar in spirit to the RDD, except you can use it from R now. So what do you get when you try to use the RRDD? So you get a bunch of things. So we mimic the Spark API for most part. So you get all of the transformations and actions that you're used to. If you're used to writing Spark code in Scala or Java, you could use similar transformations from R. But additionally, we also have a bunch of functions which make it more R-flavored. So for example, the people in this room who are familiar with R would know of lapply, which is this very commonly used function to apply a function over a list. Now that works over a list on a single machine in R. We similarly have an lapply function that applies on a distributed list, which is spread across a large number of machines. Additionally, we also have some new directives that we included. One of them highlighted that is this thing called include package. And what include package lets you do is it lets you reuse existing R packages inside your functions that you write. So for example, let's say you have a really large list, and on each partition you want to do some existing functionality. Let's say you want to compute some percentiles or something like that. Using include package, you could reuse an existing R package that computes percentiles and incorporate that into your end-to-end program. So what is your workflow going to look like at a very high level? So at a very high level, SparkR is yet another R package. It's just like among those thousands of R packages that are available out there. And you can download and install it along with your R distribution. And you can launch R, as you would usually do, and include this package at the beginning of your program execution. You can then write your program using the RRDD API that I just showed to you on the previous slide and describe what computations you want to do in terms of lapply or reduce by key and so on. And when you run your program, these RRDD actions and transformations are then compiled down into Spark jobs that are executed on your cluster. And the results from the Spark job and then are shipped back to R for your inspection. So this is all very good. Let's take a small example to walk through how this would look if you wanted to do this in practice. In keeping with the tradition of introducing a new API, I'm using the word count, which has become the canonical example for highlighting how things work. And so we're doing word count in R right now in a distributed setting. So the first line of my program is including the SparkR package with library SparkR. And I can then read in my HDFS file using this directive text file, which takes in a Spark context and the path to the file that you have. This must seem pretty familiar to those who are familiar with this Scala or Java or Python APIs that you've seen for Spark. So now that text file called returns an RDD object, which is lines. And now I can apply all of the transformations and actions that I listed earlier on this RDD object. So for example, I can do a flat map on this RDD object to get each of the words that are present in my document. And to do that, I call an existing R function, strSplit. I split by space, and I just pick up the result from strSplit, and that forms the RDD words. And then I can count how many words are there by associating the number 1 with each word and then adding up the counters for each word. So to do that, I use another lapply and then a reduce by key to do this. You might also notice that for reduce by key here, for example, I just pass in this very cryptic-looking plus in strings. And that's just reusing the existing R function to add integers. So the plus function here is just adding integers in R. And finally, you can get the result of your word count operation by collecting whatever you have done and like outputting it or displaying it on a graph or anything that you want to do. So this was a whirlwind tour of how word count would look if you write it using SparkR. Now let's look at something a little bit more complex. And to do that, we're going to go to this live demo, which is going to attempt to do digit classification. And to do this, I'm going to invite Zongheng, who's going to walk you through this part of the talk.
Thanks for having me. So as Shivaram said, we are going to go over this live demo on this very popular machine learning task, digit classification. And our plan is to use this MNIST data set, which is a very small data set consisting of images of handwritten digits. The high-level plan is to look at each training image. We look at the raw pixels and extract 2 things from it. One is this matrix A, which is the data matrix you've heard about. And each row represents a training instance, and the columns represent the specific features. And this labels B here is just similarly, each row represents training instance, and the columns represent the gold or reference labels. So I will be brave and admit that this is the fail case, as Evan refers to, because we are only looking at the raw pixels and extracting random features. But the purpose of this demo is to show that we can use SparkR to build a very simple machine learning task in short amount of code. But you can, of course, get fancier and do some very advanced feature extraction later on. So this is a linear classifier, and it's going to minimize this distance here. And it turns out there's a closed form solution here, which is called normal equation. So our plan is to calculate two things. One is this A transpose A, and one is this A transpose B. And we are going to solve for the equation. And the resulting X is going to be our model. So let's jump right in. OK. So what you are seeing here is I log into this EC2 machine running this IDE called RStudio. And before I walk you through this demo program, I'm just going to run the first part of the program because it takes some time. OK. So let's talk about the program. The first block here, we are just including the SparkR package, as Shivaram talked about before. And we are also additionally including this matrix package and this caret package that we are going to use later on. And we are going to store some utility functions, which are pretty irrelevant to the core of this demo. Next, we are going to create a Spark context using this SparkR.init function. And to recap, we are running on a single EC2 machine, and we are using 8 executors here. So this is a local 8. Once we have the Spark context, we can read in our training data using this text file SparkR API. And we are going to break it down into 8 partitions. So next, we are going to initialize randomly this W matrix and this B vector, the details of which are not too important. We are going to do some simple transformations on the pixels. And on these 2 lines, you can see we are using this broadcast API provided by SparkR. So why are we broadcasting these 2 things? So imagine each executor, when they are working on several partitions, you don't want each executor to read in the data multiple times. So that's why we push out the data beforehand. And here we are using this include package call that Shivaram talked about before. We are telling the executors that you are going to use the matrix package later on. So we call that we have our training data in an RDD of string returned by the text file function. And these 2 assignments just parse the strings and compute the random features and put in the labels. So this feature labels variable holds an RDD available for further processing. Now we come to the backbone of our algorithm. We are going to compute this A transpose A and A transpose B components. For those of you who might not know our syntax, this might look a little bit weird, but what it's doing is just transpose. It's using this SparkR API called lapply partition. And for each partition, we are doing a transpose on the features and multiply it by itself. Similarly, in A transpose B, we are transposing the features and multiplying by the label. So this returns an RDD, right? And we use this SparkR API collect to collect the results to the driver. And reduce and plus here are actually just ordinary R functions that you can use. So now the code finishes executing. Let's try to solve for the equation. So I'm just going to use this ordinary R function, which is called solve. It just solves a system of equations. And I'm going to type this out, solve A transpose A transpose B. So as you can see, we are getting back a long vector, which will just be our model. And now, as the next step of this machine learning task, you can imagine we want to read in the test data and compute the test error. So we have this code to do this. Okay, so the test error is about 5.4%. I will admit this is not a great test error for this MNIST data set. Many more advanced techniques exist that have a lower test error. But again, the purpose of this demo is to convince you you can do some simple stuff quickly using SparkR. Now we are going to do two visualizations. The first visualization is just going to plot this confusion matrix. So a confusion matrix is a very popular way to visualize a multi-class classification model. So as you can see here, the x-axis represent the reference labels or the gold labels, and the y-axis here represents the predicted labels. And the darker the grid, the less confusion there is in our classifier. For instance, it's very good to see the whole diagonal to be mostly all black. But as you can also see here, there are some non-trivial black grids floating around. For instance, the x-coordinate here is 9, and the y-coordinate here is, the x-coordinate is 7, and the y-coordinate is 9. So that means that our classifier often confuses true label 7 to be 9. So this is just one of the visualizations you can do after you train a model in SparkR. And to do this, this confusion matrix call here is provided to us by the Carrot package, and there are many more packages out there available to use. Next, imagine after seeing this confusion matrix, you might want to look at what are some of the specific test images that you got wrong. So this code is just going to pick a random test image that we got wrong. So here, the expected label is 9, but the predicted label is 4. Looks like a pretty terrible error to me. We can do this one more. So this is a 7, but the classifier got 2. I can kind of sympathize for the classifier. It's a pretty hard case. So this is the end of the demo. And in summary, what we have achieved is that we show how we can use SparkR's API in a very natural way by leveraging some of R's advantages. For instance, we show how you can do visualizations, which we believe is one of the keys to interactive data science. We also leverage this powerful RStudio IDE and some statistics functionalities provided by R, such as the solve function. And this whole demo program is available on GitHub, and Shivaram will show you the link to the GitHub repo. I'm going to hand over to him.
Thanks a lot, Zongheng. So let's get back to our slides now. And so we just saw this demo that shows you how SparkR can be used to do some interesting tasks. But the next part of the talk, what I'm going to try to do is I'm going to try to answer this question of how does this all work, or what did we need to do in order to build the system to enable things like this. So at a very high level to do this, I'll first describe the data flow that happens, or what are the how data and computation goes from your local R machines to different things on the cluster, and then we'll describe a couple of specific optimizations that make it easier to use SparkR. So when we first launch the R process in your local machine, the R starts running, and we have a bunch of worker machines on the cluster which are idle at this point. When you hit the first line that creates the Spark context, or the SparkR.init line, we correspondingly create a Spark context along with your R process. And we also use JNI to create a backing Java Spark context. This is very similar in spirit to what happens in the PySpark model as well, where they use this Py4j package to create a backing like Java Spark context. What follows is that whenever you want to perform a computation, let's say we wanted to do A transpose A or something like that, the Java Spark context then communicates with all of the worker machines, and specifically the Spark executors that are running on these worker machines, and ships a bunch of stuff which are required to run your computation to those machines. Now, each worker machine in turn receives the computation, the data description of what needs to be computed, and locally it forks an R process, which will then be used to actually perform the computation. Now, the results of the computation are shipped back in just the reverse order, where the R process hands back the results to the Spark executor, and these are then accumulated and sent back to your local R process, and thus you can visualize or you can do further processing with the data. So one of the key points that I'm going to talk about is what goes on in this orange arrow, or what is shipped in this pipe between the local machine that you have and the Spark executors that run on the cluster. So when you're writing these SparkR programs, one thing you might have noticed is that when you're writing a function, you can typically refer to variables which exist outside the scope of that function. And these will automatically get shipped and appropriately materialized in different machines that exist on the cluster. So this is this notion called closure serialization, where we need to figure out what are the variables and methods being used in a function so that we can set up the same environment to be when we're running it on different machines in the cluster. Now, to do this, what we used is that we used R's hierarchy of environments that are present in an execution context, so we can do this automatically without the user telling us what variables and what methods need to be serialized. So in some sense, we have a stack of environments that relate to every R process. And so given a user function, we can walk up the stack, and we can check if the variables being used in that function are present in any of these frames in the stack. And then we can grab the right set of variables and then serialize them and ship them out. Now, in doing this description, I use this word called, we are going to serialize them and send them out. So the next question is, how do we do the serialization? And to do this, we actually fall back on R's native serialization methods and we exploit already existing functionality to do this. So you probably, if you've used R, you've run into the case where when you're exiting R, it prompts you as whether do you want to save your data for a future session or not. And so the save command has a backing serialization routine, which can take all of the variables, or given any variables, serialize it and write it out to disk, so that when you resume your process, the same variables get loaded up. We hook onto the same functionality, and any of the closures that we are shipping, we save the variables which are there in the closure, but instead of saving it out to disk and for resuming, we ship out those variables across the network to these machines in the cluster, so that and then we can load these saved data out on the machines, and so you get back the same variables that were there in your context, in your local setup. The other interesting thing which we worked on is in optimizing this communication between the Spark executor and the R process that is run on each machine. And specifically, the case that we looked at was when you have a series of transformations, it could be pretty expensive for you to have this communication repeatedly between the Spark executor and the R process. So going back to our word count example, we saw a chain of transformations, like doing a flat map and then doing a lapply. And a naive way to implement this would be, for every such function that we hit, we fork R, we run that particular function, and then we come back to the Spark executor. So in this case, we would be forking R twice. So one of the features that we added was this notion of pipelining these functions together, or creating a pipelined RDD, which squishes these functions together so that you can fork R fewer number of times, or you can reduce the number of communication rounds that happen between the executor and the R process. So as in the previous case, the flat map and the lapply can be squished together to form one pipeline function, and thus this happens automatically behind the scenes. We just look at the query DAG that's happening, and we pipeline as many stages as possible to do the computation. So SparkR is a pretty young project compared to most of the other Spark APIs that are present out there. And there's an alpha sort of developer version that's available on GitHub. One of the things that I'm really proud of is this one-line installation command, which you can run from your laptop or any machine, and then it should fetch the package for you and install it out for you. In terms of implementation, like I alluded to before, the design of SparkR is very similar to the PySpark effort. The biggest thing that we learned while doing this is that Spark is actually very easy to extend. So the core part of Spark being pretty flexible means that we had to write very few lines of Scala code in order to make this possible. So in our repository, we only have around 329 lines of Scala code. And most of our code is in building up this RRDD API and all of these transformations and actions, and that's around 2,000 lines of R code. There's also another thing that I'm proud of is this 693 lines of test code. So our API is pretty well tested, and the coverage is pretty comprehensive. There are many other things that are available on our GitHub repository. These include scripts that can help you set this up on EC2. And we also have implementations of all of the Spark examples, like k-means, logistic regression, word count, and all of these things implemented using SparkR. And the MNIST demo that you just saw, there's code and data available for you to run that and try it out as well. And finally, we also, more recently, we just added support for running SparkR on a Yarn client mode, and also for you to compile it and run it on your Windows boxes as well. So these are a couple of new features that we added recently. And there's also a growing developer community developing around this project. We have around 300 stars on GitHub, which is a metric of popularity, I guess. And the other thing that is very nice is that we have 13 contributors, and 10 of them are actually from outside the AMP lab. So there's a growing user base, but there's also a growing set of contributions that we're getting from outside developers. We also are working with Alteryx, which is this company which makes data science products, in order to add more features, which leads me to the SparkR roadmap, or what's in store in the near future. So a couple of features that I'm really excited about is this high-level data frame API and the MLlib integration. So what we saw today in terms of this lapply model was that the RDDs are distributed lists. And lists are very powerful, and you can do a lot with them. But data frames are this sort of tabular API that's also very popular among our users, and it's very powerful to do a lot of data processing. So we want to support a distributed data frame API, and we are specifically looking at some of the schema RDD functionality that Michael Armbrust talked about yesterday, and seeing if we can leverage some of those things in order to build this kind of higher-level data frame API. And we also want to complete this integration with MLlib. So right now, you can describe your machine learning program in R in terms of these map and reduce by key operations. But once we have this MLlib integration, it'll be more of a one-line call, where you can say k-means from R, and then it'll go ahead, it'll run k-means in a distributed setting, and then return back just the cluster centers to you that you can use in your R program. And finally, as the project matures and we reach closer to API and functionality maturity, we want to merge this with the Apache Spark project and support this as a first-class citizen in terms of a Spark API. So in summary today, we presented to you this project called SparkR, which takes this high-level idea of representing RDDs as distributed lists and enabling transformations and computations on them from R. And this enables you to run R on large clusters and not be limited by the memory or processing capabilities of one machine. And in addition, lets you reuse existing packages inside your closures that you run on a cluster. And the goal of SparkR is to combine the scalability of Spark and the utility provided by using R. And today we saw some examples and a demo that show you how this can be done. Our project is on GitHub. This is a link to the repository. And we also have a developer mailing list. And I'd encourage you to send any questions or any comments that you have or feature requests that you have. And I'd be happy to talk to you after the talk as well. With that, I'll take any questions. Thank you. Yep. So the question is, how do we, so we have this mapping of RDD to lists, and we showed the example of how you can treat images and map them. So how do we map images to RDDs? So the way we did this for this demo was that the image was represented as pixel values, as like comma-separated pixel values in a file. So we took every line in that file, we parsed it as CSV, and then we created an image or a matrix from parsing that CSV from every line of that CSV. So we wrote there's a utility function that we wrote, which is parse image into a matrix. And what it basically did was it looked at the entire line and then converted all of the string values to doubles and then created a matrix out of those doubles. So it's just a user-defined function. And this is for the specific format. You can also write your own functions to parse any particular format that you want. And at the very heart of it, we're running these R functions to do the processing. So if there is an R connector which can process your format, you can also reuse that when you're doing the parsing.
Good. Maybe let's take one more question, if there is one.
Yep. Sorry, I didn't get the first part. How do we fork the R process, and what do we? Is there an API to do this? So that's a good question. So what we use is something which is extreme. It's just homegrown. So we use a Java system call API to explicitly run the R process. So it's as good as like opening a shell and running R on the worker side using it. And then we have this custom protocol of, so R basically listens on its standard input for what is the computation that it needs to run and where it needs to read the data from. And the Spark executors speak the same custom protocol. So they send out the computation first, and then the data items that need to be processed. And on the other side, we read that in. So we use like a socket or a file API or a pipe API between the two to communicate. Yeah. The question was, are there any plans to make it more general? And we would like to make it more general because it's to make it a little bit more extensible. Like if you want to add some features or to make this communication more efficient. But we're looking into what are good options. So far, this was a good way to bootstrap something and get it working. And we have, I think, a good enough solution for that. But both in terms of performance and functionality, it will be good to explore other options or other ways of doing it. But there are no concrete plans right now.
Great. Let's thank Shivaram again and Zongheng.